This video is about intermolecular forces. By the end of this video, you should be able to differentiate between chemical bonds and intermolecular forces, or IMFs. You should understand the difference between dispersion forces, dipole-dipole interactions, hydrogen bonding, and ion-dipole interactions. And you should be able to identify the major type of IMFs present between molecules. First, let's consider why we care about intermolecular forces. It turns out that the phase of a substance depends largely on the balance between the kinetic energy of the particles and the forces of attraction between those particles. Let's start by defining intermolecular forces. Intermolecular forces, or IMFs, are forces that occur between molecules. This is different from a chemical bond. A chemical bond occurs between atoms within a molecule. For instance, take these two HCl molecules. Within these molecules, we have a chemical bond holding the H atom to the Cl atom. This is a bond. This is different from an intermolecular force. An intermolecular force is the force between molecules. This force right here. It's a force of attraction between one HCl molecule and another HCl molecule. Likewise, here we have a series of bromine molecules. Recall bromine, Br, is a Hofbrinkel, so it's diatomic. It comes in pairs of 2, Br2. Notice here that we have a whole bunch of Br2s, and the solid line is indicating the bonds between the bromine atoms that hold together the Br2 molecules. So there's several of these bonds holding together the Br atoms to form Br molecules. On the other hand, we can find intermolecular forces represented as dotted lines. These dotted lines represent the forces between the molecules from one Br2 to another Br2. These are the forces acting between one molecule and its neighboring molecules. It's important to note that intermolecular forces are weaker than ionic or covalent bonds. Take, for instance, these two water molecules. If we wanted to break the bonds between the hydrogen and the oxygen, we would need to apply 463 kilojoules per mole in order to break those covalent bonds holding the hydrogens to the oxygens within the molecule. On the other hand, if we want to overcome the intermolecular forces, thereby separating one water molecule from the next water molecule, we'd only need to apply 6 kilojoules per mole to overcome the intermolecular force. Therefore, intermolecular forces, while important, are weaker than ionic and covalent bonds. Scientists classify intermolecular forces into 3 types. From weakest to strongest, these types are dispersion forces, the weakest, dipole-dipole forces, which are in the middle, and hydrogen bonds, which are the strongest. Notice, despite the fact that it's called a hydrogen bond, these are different than the bonds within a molecule. Again, these are forces between molecules. All substances exhibit some form of intermolecular force. There's always some kind of force acting between the particles within a substance. However, these forces may be very weak dispersion forces, or they could be very strong hydrogen bonding. The secret to determining what kind of forces are acting is to determine how polar the molecule is. Let's start by looking at dispersion forces, the weakest of all the IMFs. Dispersion forces result from a temporary distortion of the electron cloud, leading to an unequal distribution of electrons. This causes a temporary dipole, or a temporary asymmetry, in the electron cloud of the molecule. Once one molecule in a sample has a distortion of its electron cloud, it will induce dipoles in its neighboring molecules. Here's an animation showing the temporary distortion of the electron cloud. You'll see that as one atom, the atom on the left, it begins to show a distorted electron cloud, meaning all the electrons begin to bunch to the left side. It induces a distorted electron cloud in its neighboring molecule. The resulting positive end of the molecule on the left induces a dipole, pulls the electrons from the molecule on the right towards it. Therefore, these non-polar molecules suddenly exhibit some polarity. The polarity is temporary, and notice both electron clouds return to where they started in the end. Dispersion forces affect properties in a big way. First, it's important to note that dispersion forces occur between nonpolar molecules and between noble gas atoms. So here we have a series of nonpolar molecules. We have listed on this graph the nonpolar molecules of group 7. Recall that the molecules in group 7 are all diatomic molecules. So fluorine is F2, chlorine is Cl2, bromine Br2, and iodine I2. These atoms all exist in their molecular form. They're all diatomic molecules. Notice that as we increase the number of electrons present in the substance, the boiling point and the melting point of these substances increases. This is due to increasing strength of dispersion forces. So the more electrons you have in a molecule, the more easily distorted its electron cloud will become, and therefore the stronger its dispersion forces will be. Notice here that room temperature is indicated by the dotted red line. You'll notice that fluorine and chlorine have melting and boiling points well below room temperature, therefore they're gases at room temperature. However, bromine has a melting point below room temperature and a boiling point above, therefore it exists as a liquid at room temperature. Iodine, the largest of these molecules, the one with the most electrons, has a comparatively higher melting and boiling point, and iodine, as you may know, is a solid at room temperature. Moving on to the next stronger intermolecular force, dipole-dipole interactions. Recall that polar molecules are said to exhibit a dipole, an area of positive charge and an area of negative charge. Dipole-dipole interactions occur when the positive end of one molecule attracts the negative end of a neighboring molecule. As we said before, these are weaker than covalent and ionic bonds. They're about 1% as strong as an ionic or a covalent bond, but they're much stronger than dispersion forces. And also, unlike dispersion forces, which are temporary and induced, dipoles are permanent. You'll always have a dipole within the molecule. Taking a look here, we see that these two molecules both exhibit a dipole. They both have an uneven distribution of charge resulting from their structure. In both cases, our dipole points towards the end that's labeled in blue. Notice that the negative end of one molecule will attract the positive end of its neighbor. There are two possible orientations for this to happen. These attractions are known as dipole-dipole interactions. Again, dipole-dipole interactions, like dispersion forces, affect properties. Notice these two molecules here, CO2 and SO2. If you draw out their Lewis structures and predict their shape, you'll see that CO2 is a linear molecule and SO2 is a bent molecule. Because CO2 is linear and has dipoles pointing equally in both directions, it does not exhibit an overall molecule dipole and is therefore nonpolar. It exhibits no dipole-dipole interactions. SO2, on the other hand, does exhibit a molecule dipole. Notice that both bond dipoles are pointing downwards towards the oxygen, so our overall molecule dipole points downwards, indicating a negative end of the molecule at the bottom and a positive end at the top. This makes it a polar molecule, and it exhibits a dipole. Notice that the boiling point of SO2 is much higher than the boiling point of CO2. Because of its dipole-dipole interactions, the molecules are more difficult to separate from one another because they attract to one another. Finally, let's move on to the strongest of our intermolecular forces, hydrogen bonding. Hydrogen bonding occurs among molecules in which hydrogen is bonded to a highly electronegative atom. So when you have molecules that contain HO bonds, HN bonds, or HF bonds, you will have hydrogen bonding between molecules. This is an incredibly strong type of dipole-dipole interaction. The hydrogen bonded to the highly electronegative atom, N, O, or F, results in a very polar bond, which results in a very large partial charge differential. So the end with the N, the O, and the F of the bond will be very negative as compared to the hydrogen end, which will be comparatively very positive. This results in a very strong attraction between molecules. Here's some water molecules, for example. The oxygens are represented by the green and the hydrogens are represented by the blue. Because these water molecules contain HO bonds, these bonds are very polar. We end up with a very negative end up top at the oxygen, the green end of the molecule, and a very positive end down the bottom where the hydrogens are represented by the purple-blue color. The dotted lines here represent the hydrogen bonding that is occurring between molecules. When the negative end of one molecule attracts to the positive end of the next, we get these hydrogen bonds. Notice that the hydrogen bonds we're referring to are not the HO, the HN, or the HF bonds. They merely make hydrogen bonding possible. Hydrogen bonds are, as we said, the exact same thing as a dipole-dipole interaction, but because they're stronger, they get a special name. As you might predict, hydrogen bonds also affect properties. Here we're looking at a graph of temperature versus period on the periodic table of a number of different substances. I want you to pay specific attention to the first set of substances here. Notice these are all compounds combining hydrogen with a different element. At the top we have H2O, then HF, then NH3, then CH4. Notice the sharp difference between boiling points of H2O, HF, and NH3 and CH4. CH4 seems to be an outlier. CH4 does not exhibit hydrogen bonding. One CH4 molecule is not very strongly attracted to its neighboring CH4 molecule. H2O, HF, and NH3, however, all contain an HO bond, an HF bond, or an HN bond, causing it to be a very polar molecule that is able to hydrogen bond with its neighboring molecules. This results in an exceptionally high boiling point for each of these substances. You might also compare the boiling points of each of these substances with other substances in the same period. So H2O compared to H2S, H2SE, H2TE. These are all hydrogens bonded to atoms within the same group of the periodic table. But notice H2O, due to its hydrogen bonding, exhibits far stronger intermolecular forces, as evidenced by its much higher boiling point, than other molecules of similar structure. Let's look now at one final type of interaction, ion-dipole interactions. Technically, these aren't intermolecular forces since an ion isn't a molecule, but it follows a similar pattern. Ion-dipole interactions occur when ionic solids dissolve in a liquid, particularly water. The strength of the forces is what makes it possible for ionic substances to dissolve in polar solvents, like water. Here we see that the positive ends of the water molecules are attracted to the negative chloride ion, while the negative ends of the water molecules are attracted to and surround the positive sodium ion. That brings us to the end of this video. Let's review our goals. First, we learned to differentiate between bonds and IMFs. Then we looked at the difference between dispersion forces, dipole-dipole interactions, hydrogen bonding, and ion-dipole interactions. And then we learned to identify major types of IMFs present between molecules.